Morning. My name is Paul Sabanal. I work for IBM's X-Force Advanced Research Team. And today I'm going to talk about possible ways to create code that hides other malware, also known as rootkits, by taking advantage of the mechanisms of Android's new runtime called ART. So here's the agenda for my talk today. First, I'm going to give some background information. Then I will talk about I will give a high-level view of ART's architecture and mechanisms, as well as the file formats that it uses. Then I will follow with the main part of this talk, which is user mode rootkits, and end with a demo. So the main motivation for this research or for this talk is that there has been some recent advancements in Android security. And one of the notable ones is the Verity. And I won't go into detail about this, but it allows Android to verify the integrity of a partition at boot time. And so you can use this to detect modifications to the system partition. And it basically allows Android to protect devices from rootkits that adds or modifies binaries in the system partition, which is how rootkits in Android traditionally works. They add some binary or modify some binaries or some files in the system partition. However, this is not yet enabled by default. But as security researchers want to know what can an attacker do despite of this, even if it's not yet in active use. Also, we want to ask the question, can we conduct rootkit operations without touching the system partition? And to answer these questions, we turn to ART, which is another new technology that's added recently to Android. This is the new Android runtime that has replaced the older one called Dalvik. Basically, we are going to take advantage of ART's mechanisms to modify framework and app code without touching the system partition. Okay, before we go into the details of how to do that, I'll talk about some overview of how ART works. Okay, so ART was first introduced in Android KitKat 4.4 back in October 2013. It was still at the time, it was an experimental version, and you can select which runtime you would use. But in November last year, with the release of Android Lollipop 5.0, it became the default runtime. So if you're going to buy a new phone now with a Lollipop, that's the one that is in use. The main difference between ART and Dalvik is that it has a much better performance. It does it because of the feature called ahead of time compilation. In Dalvik, your application's code runs on top of a virtual machine. The bytecode or the code for your application will be interpreted. On the other hand, in ART, your code will be compiled ahead of time. In other words, your Dalvik bytecode will be converted into native code, which is the code that runs on the architecture of your device. So for example, if your device runs on ARM, the Dalvik bytecode will be converted into ARM code. If your device runs on x86, your bytecode will be converted into x86 code. The advantage of ART, like I said, over Dalvik is that it has better performance, since your application's code will be running on bare metal, so to speak, and also because your CPU wouldn't have to do as much like interpretation and other stuff. It will result in better battery life. And there's also some very minor drawbacks, almost negligible, but it will require more storage space than normal, because your application will be compiled into another file, which is stored separately, that contains your generated native code. And also, every time you install an application, it will be compiled, so it will take a little bit of time. This ahead of time compilation is done at first boot or the first time you boot a device you bought. and upon system upgrade or OTA updates. In this scenario, it will create a boot.oat and boot image, which I'm going to talk about later. And all the installed apps on your phone will be compiled. So this will take like a few minutes if you have a lot of applications installed at the time. Compilation will also be done upon app installation, like I said. And it will also be recompiled again every time you update an application. So ART does all this using a program called dex2oat, which you can find in the system bin directory. This tool will compile the bytecode in classes.dex, which can be found inside your application package or in one of the framework jar files. It will compile this classes.dex into native code. The dex2oat tool receives several parameters, including the location of where you have placed the file you want to compile or the application you want to compile, and then the output location, which is normally be placed in the data Dalvik cache / target architecture, or the folder name is the target architecture. For ARM, it's ARM, and for x86, the folder name will be x86. So after the ahead of time compilation is done, whenever your app is run, the code generated in the resulting oat file is executed instead of the bytecode in your dex file. So I won't go into the nitty-gritty details of compilation, but I have to mention that there's currently two types of compilation that can be done through the two compiler backends, which is quick and portable. You can choose this through the command line parameter compile backend for dex2oat, and the current default for ART is quick. So quick basically turns your dex bytecode, or in this case it's called the medium level intermediate representation. It turns it into a low level intermediate representation, and then converts it into the native code of your device. And there are some optimizations done at each stage. The portable backend, on the other hand, uses LLVM, and it converts your dex bytecode into LLVM bitcode, then does some optimizations on it, and then use one of the LLVM backends to generate code for your device. Now, I mentioned earlier a boot.oat file. This is a sort of a master file where all the most commonly used frameworks and libraries in Android will be compiled in. So it's a single oat file where that contains all the code from different framework jars in the boot class path. So these are all preloaded into the applications that you installed. So here you can see an example command line where the parameters for dex2oat, there's a --dex file. There's a lot of --dex file options, and each option will have a single framework jar, which can be found in the system framework folder. So these are all compiled into a single oat file called boot.oat. And here's a list, much bigger list of all the framework jars that is included, at least in a Nexus device that I've tested. So they include the core framework jar code APIs and some stuff for HTTP and some messaging APIs. I also mentioned earlier about the boot image. It's a file named system@framework@boot.art. This is also found in the Dalvik cache folder, and it contains pre-initialized classes and objects from the framework. It contains pointers to methods in boot.oat, and essentially your application will refer to this image every time it calls something from the framework. So So as an analogy, you can think of it as like a import table in portable executables, wherein you can access the addresses of the methods in the framework through here, and not using the address in the boot.oat directly. So this is loaded by Zygote along with boot.oat, and here's a typical layout of it once it's mapped into memory. So your applications will have a similar one mapped into its memory space. It starts with the boot.art file, and the rest of the sections of the boot.oat file will follow. Here's the file format for the art image. It starts with a magic with an art string to mark it as an art file, followed by a line feed, then a version which is currently set to, I think, 12. And the rest of the fields are just fields that describes the link boot.oat. They're also a pair. So, and also has the information about the base address of the image and size, etc. But the art image is less significant in this talk than the following, the oat file format. The oat file format is essentially just an ELF dynamic object, which is in the ELF file format. The extension used is .oat for boot.oat and .dex for regular applications. You can locate in which part of the ELF file you can find the oat-related data by looking up the dynamic symbol tables with the following names: oat data, oat exec, and oat last word. As you can see here, the sim value field of the symbol table indicates where you can find it in the ELF file. The oat data section contains headers and metadata, and also it contains the original dex file that the oat file has been compiled from. Oat exec contains the compiled code, and oat last word is just an end marker. So you can so when you say an oat file, you can just treat the start of oat data until the 4 bytes included in oat last word as a single blob. And afterwards, when I mentioned something about offsets, it means that it is relative to the start of oat data. Alternatively, you can also locate the oat data and the oat exec through ELF sections. The section named .ro data, which is read-only data, will contain the oat data, and the section named .text, which contains executable code, will contain oat exec. So this is a basic layout of an oat file. It starts with an oat header, followed by several oat.dex file headers. Each oat.dex file header represents a class.dex that has been compiled. So for normal applications, there's going to be only one oat.dex file header. But in the case of the one that I showed you earlier, in the case of boot.oat, there can be several oat.dex file headers. The oat.dex file headers also points to the embedded dex file inside the oat. So when you compile an application, the classes.dex that contains the original bytecode will also be embedded inside the oat file. So it really helps when you're parsing, because you don't have to refer to an outside file whenever you want to parse. Because we are also going to use some of the information inside the dex files itself. So the dex file header also contains the offsets to oat classes headers, which describes all the classes inside the dex, or all the classes that your application uses or the framework uses. The oat class headers, on the other hand, contains the pointers to to the out codes, the generated native code for each method that it has. Okay, so here's the structure for the out header. It starts with a magic value, and it's currently set to OAT string followed by line feed, and the version is currently 45. And it is followed by some checksums to verify for integrity checking. And then there's also an instruction set field which indicates what the target architecture was upon compilation. And currently there are 6 architectures supported: ARM, ARM 64, Thumb 2, and x86, x64, MIPS, and 64-bit MIPS. Another relevant field here is the DEX file count, which is the number of DEX files in the out file. So for normal applications, it's 1. For boot.out, can be a lot, more than 10 or 16. And the executable offset is the offset to the executable code in the out file. It is relative to the start of the out header. It's the same section pointed to by the outxx section that I mentioned earlier. Okay, and another relevant field for our purposes is the last one, which is the key value store. It's a dictionary containing information such as the command line used to generate this out file. So we're going to use that later on. Okay, right after the out header is an array of out DEX file headers, 1 for each DEX file that was compiled. So there's an important field here that we're going to use later called DEX file location data. It is the original path of our input DEX file. So it's the path to the APK or to the jar that was compiled to generate this. And there's also the DEX file location checksum, which is the CRC32 of the classes that was compiled inside that APK. A DEX file pointer is the offset relative to the start of the out header to the embedded DEX file inside the out file. Now, I mentioned earlier that it's nice to have the original embedded DEX file inside the out. The reason for this is the following: this field, the classes offsets field. It is a list of offsets to the out class headers, and the length of this list is the size. This is the class def side field of the DEX file header. So you can use the embedded DEX file header to parse the classes offsets field. So each class offset points to an out class header. And here's an interesting field here is the type, which indicates how much of the methods were compiled. You can configure your device or you can configure ART to use different kinds of criteria on which methods will compile. You can choose whether to compile everything, and you can choose only to compile all the performance intensive ones, or you can also choose to compile only the smaller, or you can all choose to compile only the ones that meets a criteria on the size of the methods. And you can look it up you can look up how to set that settings in the link shown here. So the type indicates how much of the method were compiled. So if type is, so it can have 3 different values, 0, 1, or 2. So 0 is out class all compiled, 1 is out class some compiled, and 2 is k out class non-compiled. So if type is k out some compiled, there will be a bitmap size and bitmap field following the type field. If if type is one of the all compiled or non-compiled, these two fields will not exist, and right after the type field will be the method offsets. The K-auth non-compiled means that none of the methods of this class were compiled, and those methods will be interpreted instead. If type is K-auth class all compiled, all the methods of this particular class were compiled. Now, if type is K-auth sum compiled, there's going to be a bitmap with each bit in the bitmap representing a method of this class, and if that bit is set, it means this method was compiled. And for each compiled method, there's going to be an entry in the method offsets field. So the method offset fields points to the generate native code. So now we know how to locate where the generated code for that methods are. But take note that for a K-thumb architecture, if the instruction set field in the auth header is equal to K-thumb 2, the code offset will have the least significant bit set. So for example, for method offset 001436061, the actual start of the native code is at offset 143060. So now we know how to locate the methods. But there's also some other additional information if the backend that you use is the quick backend. There's a auth quick method header right before the start of your native code. It contains a mapping between registers and IP native code and Dalvik code, and most importantly, it contains the code size of your generated native code. So if you want to take the size of the code that you generated, that has been generated for that method, you take the 4 bytes prior to the start of the generated method code. So I skimmed a lot of information here, but if you're more interested in this, there's more details in the accompanying paper that you can download from the Black Hat website after this. Okay, so let's go into the core of this talk, which is the user mode rootkits. So our approach is basically we use dex2auth to generate auth files from modified framework or app and replace the original one. We have two options. We can replace framework code and generate a new boot.art and boot.auth and replace the system generated one. Or we can replace a specific application's code and generate new auth for that and replace that installed application's auth file. And obviously we require a root shell to do all this. Okay. So the advantages of this approach is that there's no low-level code required. Our code modifications are all done in Java, so there will be less problems encountered compared to doing all of this in a low-level code or doing all of this in the kernel. Another advantage is that our techniques is less affected by variations in architecture and OS version. The same approach works regardless of the ARC and iOS and in the OS. The reason for this is that we are simply using the dex2auth itself or the art itself to generate our code, so there's less space for errors. Another advantage is that we don't have to deal with code signing at all. Since your apps are already installed, it's already verified. All we have to do, all we're doing is change the code that has been taken out and compiled outside of the applications package, so we don't have to deal at all with code signing. Also, in these techniques, our code runs under the context of the app running it. So it will have the same UID and app permissions automatically. For example, If our code is running under the Settings app, your code will have a system UID, and you can obtain permissions that you wouldn't normally be able to obtain if you're running as a regular app, such as the ability to reboot, the ability to write secure settings and unmount file systems, or to clear an application's user data. So how about persistence? Our code persists for as long as the out file is not replaced. Well, duh. The out file is only replaced, like I said, whenever you do an OTA update, or whenever that the out for that application or that application is updated. But our goal is not to maintain root access because our goal here is not to write the system or not to have anything to do with system partition at all. And the normal rootkits will maintain root access by modifying some files in it or adding some files on it. But we do have the option to reacquire root access using a system to root exploit if your code is running under system privileges. But this is left as an exercise to the reader. Now, our first option is to replace framework code. Here we replace a framework jar's code with our own. Then use dex2out to generate a new boot.art and boot.out that includes our modified jar. If you remember earlier, I showed the command line for dex2out when generating boot.out, and there's a lot of dex/-dex file parameters, and you could replace one of those jars with a version that contains your modified code. Then after you have generated your own copy of boot.out, you can replace the old one with it. So for our purposes, because you want to create a rootkit, you want to hide running processes, hide files, and hide installed apps, and probably more. So here's some of the methods that we could target. If we want to hide a running process, we could replace or modify the method getRunningAppProcesses, which can be found in the Activity Manager class. And the source code for this can be found in the ASP under the frameworks base core folder in the Java source file Activity Manager. When compiled, this will be inside the framework.jar file, which can be found on your device in system/framework. If you want to hide installed app, you modify the get installed applications method in Application Package Manager. This can also be found under the same folder in ASP in the Application Package Manager Java source file, and the result is also inside framework.jar. If you want to hide files from, for example, a File Explorer application, you can replace the method file names to files in the file class in the source file found in ASP in libcore luni in the file.java. This, on the other hand, will be placed in the core libart.jar file. So, as an example, let's look at how to hide a running process. As I've said, we replace getRunningAppProcesses, whose source code can be found in Activity Manager.java, and the build results are in framework.jar. Now, here's the original source code for that method. So as you can see, it simply returns a list of running app process info class. This class contains information about the running app process, including the process name for that running application. So we need to modify the list that it returns. So here's a modification that we did. We simply iterate through the list before it is returned and remove the entry for the application that we want to hide. In this case, com.pulse.bad app. Okay, after we have done the modification, we have to build the modified code, and not because we are going to use this modified framework.jar as the source for dex2auth, but we need to get we need to get the smally code or the bytecode for this. We can't use this as the source for Dex2auth because it might have your version that you compiled may have some incompatibility problems with the other jar files installed on your device. So what we're going to do is take out the framework.jar file on your device and modify that instead. So we use APK tool to decode the resulting jar and locate the generated smally for the method that we modified. And we're going to use the generated smally later to replace the original one. So you can automate all this, but here's how to do it manually. And you can do this on your device using ADB. But make sure it's a rooted device though. So step one is you modify the target method. You take the smally generated here earlier and replace the one in the jar file installed on your device. So you pull the original jar from the system partition, use APK tool to decode that jar and generate smally code, then look for your target method inside the generated smally, then replace that with the smally code or with the smally code for the method that you generated earlier. And after you replace it, you rebuild the jar using APK tool. It doesn't matter if the jar that you rebuilt is not 100% the same with the one that you pulled, aside from the code though. The only important part of this is the classes.dex. The resources are not important. So after you've done that, you have to rename the jar such that the resulting path after you have pushed it to the device is the same length with the path of the original jar in the system partition. Now, why do we have to do this? We need to the auth file that we generate only requires two parts that has to match with the old one. That is the path of the source APK or jar, which I mentioned earlier, the dex location path data field in the auth class header. It has to match with the original one. And also the checksum for the class.dex, which is the auth location file data checksum field in the auth class header, also has to match with the original one's match, or else we will fail. Dex2auth will not compile your modifications. So since we need to replace the path in our generate auth file with the original one, we need to make it the same length so we don't have to relocate some offsets or move, we don't have to move around stuff and recalculate the offsets in the subsequent fields of the headers. So we need to make it the same length so we can just patch it later on as is. And then we should also get the checksum of the original classes.dex, which is also we will patch to the auth file later. Now, after we've done that and we've pushed the modified jar into the device, we delete the original boot.auth. Then we retrieve the command line used to generate the original boot.auth. We can get this from the key value store field in the auth header. If you remember, there is a key value store field there. That's a dictionary that contains the command line used to generate the boot.out. Now, after we have retrieved the command line, we replace all references to our target jar with the path of a modified jar. So in this case, you see here the red ones used to point to /system framework /framework.jar, like the other dex file parameters. And you have to replace all reference to that into the location of where we pushed our own modified jar file. Now, after you've done that, you run dex2out. Now, if all that was successful, we need to take that boot.out again, because we have to patch the path and the checksum in the dex file location data and in the dex file location checksum. After we have patched, we return it, we push it again into the device in its original location. Then for the changes to take effect, we have to restart Zygote or restart the device. You can do this by using the following command: stop Zygote, then start Zygote. After you've done that, all your installed apps will be recompiled. But one downside of this approach is that if you have a lot of apps installed, the user will normally notice what you've done, because there's going to be a sort of message that says compiling apps or something like that. But our next option won't have that downside, because here we are replacing a specific app instead of a system framework jar. It affects only a single app, so it's less intrusive than replacing boot.out. The downside is it only affects the apps you specifically target. So if you only target a single app to hide your malicious applications, or when the user uses another app, your changes will not take effect. Also, apps are updated more frequently, especially user apps. For system apps, not so much. On the other hand, on the previous approach, which is replacing boot.out, apps are updated only upon device upgrade or OTA updates. So your changes will persist longer. Okay, so let's look at an example of replacing app code. So in this example, we are going to replace the code in the settings APK. This is the settings APK is you can find it usually on your Android device. It's installed as default. It shows the running processes and installed apps, among other information. And you can find the original APK in the system partition in prev settings.apk. The source code for this can also be found in AOSP in the package apps settings folder. So, for example, if you want to hide our app from the running processes list, we look for calls to the get running app processes. Then we modify the returned running app process info list. So, for example, this is the code that's responsible for that in the settings app. So here you see it's calling the get running app processes and place the list of running app process info in the processes variable. And so once it's called that, we modify the processes variable and we remove our application. We iterate through it, and if one of the application running app process info matches our application's name, we remove it. Now, to hide our app from the installed apps list, we look for calls to get installed applications and modify also the returned application info list. And here's an example of that. The code responsible for this, it can be found in the application state.java in the settings source code. So here, we also iterated the returned list of get installed applications, and remove the application info for the malicious app that we installed. Because to do this manually, the steps involved is almost similar to the ones in boot.auth when we generate the boot.auth with a few differences. So we pull the original APK from install location and use APK tool to decode the APK and generate smiley code. Then we use the modified APK here earlier and rebuild that APK. Then, as we did with the boot.auth, we rename the APK such that the resulting path after you have pushed it to the device is the same length with the path of the original APK. So we simply added some characters before the name, the settings.apk name, so that it matches the length of the original path of the settings APK. And also we get the checksum of the original class.dex. And then we prepare to run dex2auth. We delete the original auth file and push our modified APK to the device. And now it's time to generate our auth. The command line involved here is much simpler. You can also parse the original auth file and parse its key store value field to get the command line used to generate it. But you can also do a simpler way here, which is you assign our modified APK's path into the --dex file parameter, and then put the original auth file's path, which is in the Dalvik cache folder, into the auth file parameter. So here's an example of that dex2auth command. So if that was successful, we could then patch the generated auth file's dex path and checksum, like we did before. Then we restart the app. We do that by stopping the app process, or if it's running. We do that by using the following command, am4stop, then the package name of the application. So the changes will take effect the next time the app is run. So these techniques have several limitations, which one of those is we can't hide from lower level or non-framework code. So if our changes are made into the framework, we can't hide it if the application that lists running process or installed apps does not use or have an alternative way of listing it. Also, some SE-Linux policies may be able to solve us, but it's not a problem if you can set enforce, or you can set SE-Linux to permissive mode, even momentarily, because if you do that, the next time you reboot, it will return into enforcing mode, but that wouldn't be a problem, because at that point your changes have already taken effect. Also, I mentioned this as an advantage earlier, but this can also be a disadvantage. Your code is bound by the affected app's permissions, so you can't do anything that's not allowed under the context of the app that you have affected. However, since you can use this rootkit in conjunction with another malware that you wrote that has the permissions that you want to do, and you only use this rootkit to hide it, and that's the workaround you can do around. Okay, it's time for a demo. So here I'm using a Genymotion image with Google Nexus 6 and Android 5.1. So this is a bad app, which contains a picture of a handsome guy. And we are going to hide this. if you open settings here, like you can see that bad app is shown in the downloaded list, and in the running process list you won't see it here because it's in the background. But if you show cache processes, you can see that it is running in the background. Then if you look at all the installed files list, you can also see that it is installed. Okay, so we're going to do this. We have to run this tool. We are assuming a scenario wherein an attacker has access to your device and plug it in to his laptop, and he has installed a malicious application and now going to hide it from view. Okay, so let's do it. So here I'm pulling the settings.apk from the device. And I'm decoding it using APK tool and modifying all the files, the hiding processes thing and hiding installed application thing. Then I rebuild it and now pushing it to the device. Okay, so now here I'm using Dex2O to generate a new settings.out. Patch it, then push it back and restart the application. By the way, I'm using an emulator here so it can be easier to show as a demo, but I also have an actual device, Nexus 7 device here, so if you want to see it in action in an actual device, you can just approach me later on. Okay, so let's see if it was successful. Hopefully the demo gods are in my favor. Okay, so let's open the apps. Okay, so you can see here, the bad app is not shown anymore. And if you look at the running tab, at the show cache processes, you'll see that you can see it's not visible anymore in this tab either. And then if you look here, you won't see it at all. So to make sure that it's running, I didn't hide it from the recent apps list. So here you see that it is still running. But if you look at the settings apps list, it's not running at all. Okay, so that's it for the demo. Okay, now we have come to the end of the talk. To conclude, I have shown you that user mode rootkits are possible through ART, and not only for offensive purposes, but you can also use these techniques for RE as well. You can use these techniques to do instrumentation on whatever you're analyzing. And we also seen that we can still achieve persistence on the device just as long as your OAT file is not replaced. And also I would like to mention that ARP is still very ripe for more security research. And I know of only one more research that involves fuzzing the compiler in an upcoming conference. So I hope that and also, ART is still in active development. In fact, just a couple of weeks ago, Google released 5.1, and I had to change some details in this presentation and in the paper. So there are still a lot of changes being made, and some of those could be security implications. And I hope that this talk made some of you more interested in doing this. So any questions? Yes.
In user mode, with
Yeah.
that capability, can I sniff other applications running as that user only, or what can I do?
I think there's a research where I don't remember when, but they used the binder to do that. Yeah, it's possible.
So you can stay resident as long as you want.
Yeah, as long as it's not replaced, as long as not the app's
As
not.
long as they don't replace.
Yeah. You can also use this for the stuff that was that exposed and CD substrate, but those stuff are mostly used for changing the UI and stuff. But if if the changes that you want to make is just code only, you can use these techniques as well. Okay, any more questions?
So there's no signature checking on the Delta cache.
Excuse me?
There's no signature checking for signing of any of the.
No. The application is already installed. Signature checking is done upon installation. So it's already installed and it won't go through that at all.
Do any of the security applications for Android devices like Lookout or anything like that do circular checking? Do they say like, okay, this is what it was when it was installed, it's a week later, is it still the same? They don't do any kind of integrity checking?
I'm not sure. I haven't looked into the security.
Install the security Lookout on that. Would it detect that there was a process hidden?
Well, probably. But yeah, I haven't looked into how security applications could detect this. But I think they run at a lower level. I'm not sure. Yeah.
A device that will have this will need to be rooted, right?
Excuse me?
It will be needed that the device is rooted, correct?
Can I have a microphone? I can't. Oh, yeah. Yes, it is. Okay. Thanks.
I was just saying that to execute this on the device, you will need to root it, right?
Yeah, you have to initially have
it rooted.
Yeah.
Unless you root it, this is not going to get executed on the device.
No, you have to have root at first. Yeah. But you don't need root to persist. Since you don't write to the system partition, you don't have, at least in this talk, we have no option to persist as root.
Okay.
But our changes will still take effect. And if our code, for example, if I replace the settings application, our code will be running a system. And if you have a system to root exploit, which is much easier to achieve root than just a regular user, you can re-exploit your device and achieve root again, but although not persistent root.
Okay. Thank you.
Question? Good? Thanks for listening. And if you have more questions and if you notice some mistakes that I made, you can contact me through the following channels. Thank you.